So what are the states of matter? Well, there are three states of matter that we're going to be really interested in over the course of this lecture series. And these are solid, liquid, and gas. So let's think about these in a little more detail. So we have our solid. This is a diagrammatic representation of our solid. Our atoms are all packed in quite tightly. So we know that it has a fixed shape and a fixed volume. So if I freeze an ice cube, it will have the shape of the ice cube holder. So it will be a cube. And this is at a certain temperature and pressure. So we know that we can control what state of matter we're going to get by temperature. For example, if I fill up an ice cube tray and I put it in the fridge, it's going to stay as liquid water. If I put that same ice cube in the freezer, I'm going to get ice cubes. It's going to freeze. If we think now about a liquid, we know that it has a fixed volume. So like I said, with the solid, it has a fixed shape. So if I put that ice cube in my drink, it's going to stay square until, if it was at a constant temperature, it would stay square. If I took a bottle of Diet Coke and I tipped that into a glass, my liquid would now take up the shape of the glass. So it has a fixed volume. It's still going to have the same amount, but it's going to take the shape of the container that I put it in. It's quite fluid. It can move around, hence I can tip it from one container to another. And again, this is at a certain temperature and a certain pressure. If we now think about gas, well, we know that it's also fluid. It moves around. We can't see it as much, but we can move it around. And it spreads out to fill whatever space it's in. So it no longer has this fixed volume and it no longer has this fixed shape. So it will spread out to fill the container. So if I put it in a stoppered conical flask like I have here, it will have this volume, but if I take off the stopper, it's going to fill to expand the room and it will have the volume of the room. So let's just quickly look at some characteristics of some liquids and gases and solids. So we said that it has a definite shape. For a solid, it can resist this deformation. Liquids have no definite shape, so they assume the shape of the container. And then gases fill the container completely. We can't really squidge a solid, so we can't compress it. It has no compressibility, or it's nearly incompressible. If we have a liquid, we can slightly compress it, but gas, we can squidge it to fit into a smaller container. There's some densities here, so usually higher density than liquids. Liquids have high density and gases are low density. Solids are not fluid, they don't move around very much. Liquids are fluid, gases are also fluid. Solids can have an ordered arrangement of molecules. They're packed quite close together, so they tend to order in a nice fashion. Liquids tend to be disordered and have clusters of particles, and gases consist of extremely disordered particles, and there's much empty space in there. If we think about how much things can move, we can have particles can have vibrational motion only. So they just can move a little bit within space. They can't move lots of way. Liquids, they can move in 3 dimensions, but they might collide with each other. There's still a chance of meeting another molecule. And if we think about gas, they can have rapid, random motion in 3 directions. So how can we think about this in terms of something a bit more exciting? So let's think about a concert. Right? So this is an outdoor festival that happens to be download, and we can see the same states of matter at a concert. So if we look at the very front of a concert, people are densely packed. There's not much dancing room. You can maybe bounce up and down and jiggle, but you're only going to vibrate with those around you. You're quite densely packed. So this is like our solid, right? If we think about the middle of our festival, and there's a little bit of more room, we can dance around a little bit, but there's still quite a high chance that I'm going to bump into somebody as I jump around and I dance. So this is more like the liquid. And if we go to the very back of the festival, there's a lot more space. We can jump around a lot. There's plenty of room to move, and there's not much chance that I'm going to collide with somebody else. So this is more like the gas phase. So you can see, we can see how we can think about the crowd being densely packed near the front, less densely packed, but still quite a lot of people in the middle, and fewer people and less densely packed in the back. So now that we can think about that, we have that in our head, we can start to think about these things in different ways. So first up, let's think about a solid. So if I have all of these atoms, they're all quite close together. And if I have something like sodium chloride, so this is sodium chloride, the gold colored atoms are sodium and the green colored atoms are chlorine. So just nice table salts. If I look at that, we know that that's a solid. If I look at that under, if I could get close enough so I could see what exactly the atoms were doing, I would see that they line up together in an ordered array. So every time I look at a chlorine, it's surrounded by sodiums. And if I look at a sodium, it's surrounded by chlorine. And if we boiled that down to the smallest repeat unit, so if we looked at the whole big pattern and we can boil that down to the smallest repeat unit, we call that a unit cell, and that's what's shown here. So you can see, in order for me to be able to keep repeating this, I have to start at one chlorine and another chlorine, and then from chlorine to chlorine and chlorine to chlorine. And if I stacked all of those up on top of each other in 3 dimensions, I would end up with this ordered solid. And we call this long range order. Solids don't have to be crystalline. Most solids are or have long range order. What we can also have is situations where we don't have long range order. So if I looked in this little region here, I can see that my silicon, in this case in the gold, and my reds are my oxygen. You can see actually there's quite an ordered array here. But if I look wider out, you can see that that order dissipates. And we call these things like amorphous solids. So what this means is they lack long range order. So they have pockets of short range order, but they don't have the long range order. And this is something like glass. Glass has no crystalline structure. And crystalline structure will become important as we go through the rest of the year and through into next year, indeed. So we need to think about how we now move between these 3 states of matter. So we've got our solids, liquid and gases, and we refer to these as phases. So if we want to have a phase change or a phase transition, this is essentially the change between one state of matter to another state of matter. And in order to do that, we have to overcome the attractive forces that are holding it together. So we need to either put energy in or take energy out so that we can make those attractive forces or break those attractive forces. So if we look at something like our solid, which we have here, we know that if we heat a solid, it turns into a liquid. And we know if we heat it some more, it turns into a gas. And that if we go back the other way, we can take our gas to our liquid, to our solid again. And of course, a good example of this that everybody knows is water. So H2O. If we take our ice at 0 degrees C, we melt to form water, and at 100 degrees C, we boil to form water vapor. And what we need to remember is that this occurs at atmospheric pressure. This is 1 atmosphere. So here's a question. So do you think that all water molecules enter this vapor phase simultaneously? So if I hit 100 degrees, does my whole liquid just dissipate straight away and become a liquid, become a gas, sorry? And normally this would lead to some class discussion, perhaps some putting up hands to see who can answer that, perhaps some suggestion, but we can go to the answer here as I can't see the Q&A quite so easy when I'm in the share screen mode. So the answer is no, because some of the molecules at the surface, they have enough energy to escape the surface before we get to the boiling temperature. So they're able to overcome and escape into the vapor phase. And this is our interface between the air outside and our liquids. So they start to escape. And just like that, when we go the other way, some materials condense before we get to our boiling point. So we need to think about, we said a key thing there. We talked about pressure, and we said that that was under atmospheric pressure. So we need to think about what happens when we start to have pressure in the system. So if we heat a liquid and we heat it, it becomes a gas. So, okay, what happens if we take a gas at constant temperature and we compress it? So again, this would be a point where we would take some answers from the class and see what they would be able to say. And of course, the answer is, as we compress it, we go to liquid. And this is how we get to things like liquid helium, which we then use in MRIs or other medical devices. We take helium gas and we compress it to make a liquid. So that means that now we have two axes that we can start to consider. And what we can start to think about now is what we call a phase diagram. And a phase diagram tells us the temperatures and the pressures that each of those phases adopt over which range. So we can start to understand for a chemical component whether we would expect it to be solid, liquid, gas under particular conditions. And this is really important if we're going to use this industrially. If perhaps we want to use a liquid to dissolve something in, it's very important that we know what temperatures its liquid is at, or if perhaps we need a gas to power a gas turbine or something, we need to know these things. And what we end up with is pressure, which you'll sometimes typically see in atmospheres, but also in pascals is more also common, depending on when the phase diagram was published. And we have it against temperature, which typically is in Kelvin, but again, you may see it in degrees C. And what we end up with is a region of the phase diagram, which is our solid, a region of our phase diagram, which is a liquid, and the region of our phase diagram, which is a gas. And so I can say at this temperature and this pressure, I would expect my material to be solid. So let's look at a phase diagram. Here's the phase diagram for water. We can see that we have pressure along here, we have atmospheres, and then we have our temperature along here, which we have degrees C. And we can see that at melting temperature, we're on this line here, which is our equilibrium between ice and water. And we can see here, if we draw another tie line, these are called tie lines, at 1 atmosphere and 100 degrees C, we're on this line here, the boiling point of water. So the eagle-eyed among you will see, if I just flick back, this diagram has this solid liquid line going this way. However, however, the water one has it going this way. So why is that? Water's very unusual, and this is very unusual. Most materials have positive slopes, but water actually has a negative slope. So if you put into your ice cube tray your water again, and you also put another liquid in a different ice cube tray, when you put those in, the one with water will expand. So it has a larger volume when it takes the ice than it did as a liquid. Whereas most liquids have a smaller volume, they contract as they freeze. And the reason for this is hydrogen bonding. So water makes a nice network of hydrogen bonds. It actually means that ice has a bigger volume than the liquid, the water. So there are two other really important points on this phase diagram that we need to talk about a little bit more. So we can see here, this is called the triple point. And at the triple point, we have solid, liquid, and gas all in equilibrium together. The other important point is this point up here. So this is above a temperature and a pressure, we get to the critical point. And above this, we have what's known as the critical region. And we'll come on to that in a couple of slides time, and we'll talk about the critical region a little bit more. But these are important things you need to remember. So let's look at another phase diagram. Actually, phase diagrams can be a lot more complicated than just solid, liquid, and gas. So if we look here, we have what is the phase diagram of sulfur. And you can see that we actually have two different solid points. So both this area here is solid and this area here is solid. And the difference between these two solid areas is the crystal structure. So those arrangements of atoms that we were talking about are slightly different. So that long range stacking order is different between the two. And you can actually see this visually if you look at sulfur when it crystallizes. It's very pretty. If we look at the orthorhombic form, it has these cube type crystals that grow. If you look at the monoclinic form, they grow as needles. So we can actually see the difference between those. These are known as allotropes. So many things have allotropes, such as allotropes of carbon, where we know that carbon can adopt lots of different structures as well. We have liquid, and then we have our gas here. So the big question is, where is the triple point? I can see lots of places where I have multiple phases in equilibrium. Well, the answer to this question is that the triple point is still the point where we have solid, liquid, and gas in equilibrium with each other. So here we have solid, solid, liquid. Here we have solid, solid, gas. So the triple point is still where we have solid, liquid, gas in equilibrium. The three different phases, we can have multiple points where we have multiple equilibriums, but there is only one triple point. We can also go back and look at our phase diagram of water. And what we can actually see is we looked at this bit down here, which was nice and easy. We just had ice, liquid, and gas. But actually, if we look quite a lot different, we see that at high pressures, we have lots of different forms of ice. So water can form lots of allotropes as well. And there's a lot of work being done to study these materials because it gives us understanding of how space evolves and things like that. We can actually access some of these at high temperature and high pressure. And people dream up really exciting experiments to try and find out the different structures of these materials. I promised you that we would come back to the critical point. And if you look here, I said the critical point was above that point, we end up in the critical region, so above a given gas and pressure. And what we end up with is if we end up with a state which has the properties of both a gas and a liquid. So we end up with one indistinguishable phase. As we move along that solid liquid gas line of the phase diagram, if we were to look below the critical point, we would see two distinct phases in equilibrium. So we would have the liquid and we would have the gas. As we increase both the temperature and the pressure, this distinction becomes more and more blurred, as you can see here, and we end up with what we call a supercritical fluid. So it's one indistinguishable phase. And supercritical fluids are really exciting because we can actually get properties of both gas and liquid, like I said. But that is really interesting. So this is some work I did a very, very long time ago now. But we took a membrane, which you can see here, which has lots of holes in it, and we wanted to grow materials in them to make new electronics devices or new exciting ways of doing things. We were looking to make some wires, and we were looking to make them so that they had a core and a shell. And using supercritical fluids, we can dissolve the precursors that we wanted to use in the supercritical fluid as if it was a liquid, so we can dissolve, make a solution. As we pass it through our porous material, our material with lots of holes in it, it behaves more like a gas. So the gas flows through the holes much easier, and we're able to grow these very pretty nanowires. So just some key points with just some key points on phase diagrams before we move on. So we know that boiling point increases with increasing pressure. So these are some important things we need to remember. We know that melting points usually increase with increasing pressure, but there are some examples that don't do that, some exceptions, for example, water. And we know that many systems exhibit polymorphism and show allotropes, such as our sulfur, and we were talking about carbon.